Vectors and projectile motion. So in 2020, in the higher level question, we had a cricket player moving her hand away from the motion of the ball as she catches it. We're told she then throws the ball upwards with an initial velocity of 28 metres per second at an angle of 45 degrees to the horizontal, and her hand was 1.6 metres above the ground. A short time later, the ball was caught by another player, and when it was caught, the ball was again at a height of 1.6 metres above the ground. So it was caught and thrown from the same height above the ground. So the first thing we have to do is calculate how long was the ball in the air. So to do these questions, what we need to do is have a look at the fact that the ball, if we look at the motion of it, is going to go up through the air, and we get this kind of projectile motion. So it's like this parabola traced out by the path of the ball. And again, it's going to be caught at the same height that it was thrown from, which we know is 1.6 metres above the ground. And if we're looking at from where it was thrown to where it was caught, we call this distance the range. So basically this is the distance in the x direction. So we have to make out a table, and we are used to doing this in applied maths. We don't generally do it that often in physics, but I'm going to show you how to make out the table to look at velocity in the x direction and in the y direction, distance in the x direction and the y direction, and acceleration in the x direction and the y direction, and therefore the equations v equals u plus at and s equals ut plus a half at squared in both the x and the y direction. In other words, we have to resolve this into the x and y components because of this angle 45 degrees to the horizontal. So in other words, if I was to mark that out on my diagram, we have 45 degrees. So if I was to look at any point along that path, let me draw this diagram down here at the bottom. At any point, if I mark the blue, we have the ball, we can see that the velocity vector that it was launched at, so its initial velocity, is 28 metres per second. So at every point along that path, we have velocity in both the x direction and in the y direction, and the resultant can be found by Pythagoras at any point along the path. So we say that the velocity vector can be written as v cos theta in the x direction and v cos theta in the y direction. So I'll do it like this actually. So we normally call these I and j vectors in applied maths, but for the purpose of physics here, I'm just going to keep it in terms of x and y so you understand what I'm referring to. Okay, and again, sorry, this should be sine theta. And again, where we're getting those from is resolving that vector, which we looked at in the vector video yesterday, okay? So in other words, if I have v as my vector at any given angle, then by drawing the perpendicular and parallel components to each other, we have these two vectors are equal because they are the opposite sides of a parallelogram, which gives me the opposite side, the adjacent side, and the hypotenuse. And therefore what we have is the opposite is always the hypotenuse times sine theta, and the adjacent is always the hypotenuse times cos theta. So the adjacent we can see is in the x-axis direction. So therefore that's v in the x direction. And the opposite is in the y direction. So that's our y component of our velocity vector. So what we get then is this table where we have initial velocity, acceleration, velocity, and s in the x and in the y. And we can make out this table. To look at velocity and acceleration in the x and the y direction. Now, the acceleration of any object in projectile motion is going to be in a state of free fall. So in other words, it's due to gravity. So gravity is always acting down on the object. So if I have the object here, we're going to have gravity acting down. So therefore we can see there is only gravity in the y direction. There is no gravity in the x direction here because it's starting and landing in the horizontal plane. So therefore acceleration in the x direction is 0. Initial velocity we can see is going to be in the x direction, u cos theta, and in the y direction, u sine theta. We can see that from up here. Because the initial velocity is thrown upwards and gravity is in the opposite direction downwards, then gravity has to be given a negative sign because it's in the opposite direction to the initial velocity. Okay, we know that v is equal to u plus at, so velocity in the x direction is u in the x direction, which is u cos theta, plus at, well 0 times t is going to be 0. Velocity in the y direction is u sine theta minus 9.8 t. S in the x direction, well s is equal to ut plus a half at squared. So u in the x direction is u cos theta t, and then 0 for a makes a half at squared 0 also. S in the y direction is going to be u, which is u sine theta, plus a half at squared. Well, that's going to be minus a half times 9.8, so that's minus 4.9 times t squared. And of course, t is just going to be t in both cases, so it's our time. Now, of course, we know in this case that u, the initial velocity, is 28, and we know that theta is equal to 45 degrees. So if I go to that diagram, I can mark in 45 degrees on that. So if theta is 45 degrees, then I could actually rewrite this whole table. And I could say it's u cos 45, u sine 45. In other words, 28 times sine 45 and 28 times sine 45. So we can actually sub those in. So you could actually write out that table in terms of u 28 meters per second and theta being 45 degrees. Okay, so I'm keeping it in terms of the formulas here for the moment. So the first thing the question asks us to do is, how long was the ball in the air for? So we know that basically it's going to start here, which was 1.6 meters above the ground, and land over here, which was also 1.6 meters above the ground. So basically on landing, we can see that the displacement above the horizontal is actually 0. So it hasn't actually changed its height above the start and end position. So what we say is, on landing, the displacement in the y direction is equal to 0 because it starts and ends 1.6 meters above the ground. So sometimes these projectiles start on the ground and land on the ground. Sometimes they start above the ground and land below the ground. So in this case, it's starting and ending exactly the same position. So there is no change in displacement in the y direction. So if we go back to our equation there, we have u sine theta minus 4.9 t squared. So sy was u sine theta minus 4.9 t squared. And we're going to let that equal to 0, where u is 28 meters per second. Theta was 45 degrees. There should be a t there, equals 0. So that's u sine theta t, sorry. Okay, so we can see t is common. So if I take out t as being common, that leaves me with 28 times sine 45 is 1 over root 2 minus 4.9t equals 0. And that means that t must equal 0, so that would be at the start. So the displacement is y at the start, but also at the end. And we have 28 over root 2 minus 4.9t also must equal 0. So that means that we have 4.9t is equal to 28 over root 2. So in other words, t is equal to 28 divided by 4.9 root 2. So our time, which we call our time of flight, is equal to 4.04 seconds. So we refer to this as the time of flight. So in other words, the time spent travelling. So time the ball is in the air. So there was 3 marks for our equation and 3 marks for getting our answer there. Okay, so the second part of the question then for this calculation says, what is the horizontal distance travelled by the ball? So that's our displacement in the horizontal direction. In other words, if I go back up to this diagram here, that's our range. So in other words, the distance travelled in the x direction is the horizontal direction. So that's s of x, okay? So s of x we saw was u cos theta t. And basically, the time it takes to go from the person throwing the ball to the person catching the ball is the same time that the ball has been in flight for. So in other words, at this point we saw sy was equal to 0, and also at the start sy was equal to 0. So that means that the time when s of x is over here is the same time for the time of flight, so 4.04 seconds. So basically our range is going to be u, which was 28, cos theta, which is 45 degrees, times the time of flight, which is 4.04. And therefore that gives us a range of 79.99 meters, or if you're rounding that, 80 meters is also acceptable. And again, there was 6 marks going for that, so 3 for setting up our equation and 3 for our answer. Now the next part of the question then says, well, what is the maximum height above the ground reached by the ball? So the maximum height, let me mark it in green here, is going to be the highest point along the projectile path. So in other words, we're looking for the distance in the y direction. But when is that going to happen? That's going to happen when the ball is at this point, and at that point it is only going to have velocity in the x direction because the ball is still travelling to the right. But there will be no velocity in the y direction. So in other words, at this point, the velocity in the y direction is 0 because it's at its highest point. So in other words, as the ball is travelling from left to right here, that velocity vector in the y direction is getting smaller and smaller and smaller until we reach the highest point, and then as it begins to fall, that velocity in the y direction would actually change direction because it's starting to fall. So we say the maximum height, or the greatest height, occurs when the velocity in the y direction is 0. So if I look at my velocity in the y direction, if I go back to my table, that's u sine theta minus 9.8t. I'm going to let that equal to 0. So u is 28. Sine theta, well, that's sine 45 degrees. Minus 9.8t is equal to 0. So the time when that happens is going to be 9.8t is equal to 28. And sine 45 is 1 over root 2. So that's going to be 28 over root 2. And the time at which that happens is going to be 28 divided by 9.8 root 2. So the time for the greatest height is 2.02 seconds. Now what's interesting to note there is that is actually half the time of flight. And that's because this is a symmetrical journey. So in other words, if the time of flight is 4.04 seconds from start to finish, then to reach the halfway point, the greatest height, that's going to be half the time of flight. So now we know that the time of flight is going to be 2.02 to reach the greatest height. Well, we can say sy if I go back to my table, is u sine theta t minus 4.9 t squared. And if we sub in again, our initial velocity was 28 sine 45 degrees, time taken to reach the greatest height. And if we simplify that, that gives us our greatest height, in other words, s in the y direction, which gives us 19.999999, so in other words, 20 meters. But if we go back to our diagram, we have to remember, if I mark it over here in purple, that it actually started 1.6 meters above the ground. So therefore we have to say, well, it's actually the maximum height above the ground, not above the person's hand. So we have to say, well, we've just found SY is 20 and we know it's 1.6 meters above the ground. So therefore the greatest height above the ground has to add on that 1.6. So in other words, the greatest height above the ground is 21.6 meters. And again, we had 3 marks for setting up our equation here and 3 marks for our answer. So of course we could have assumed the 2.02 from our previous answer.